7.2 on sample proportions. This first page called the Candy Machine. It's an in-class activity that we'll do together to explore what happens as you change your sample size and as you change your number of samples. So that's something to look forward to in class. The second page here, talking about the formulas that can be found on your formula sheet for sample proportions. And P is going to be the symbol that we're going to use to represent a population proportion, and P hat will represent a sample proportion. When you are taking a sample of size, if you're taking a sample of size n from a population, you can count the number of successes and divide by your sample size, and that will give you an estimated value, that sample value P hat. And if you were interested in doing a sampling distribution, which I'm not saying that I necessarily would be, but if I wanted to do a sampling distribution, recall that a sampling distribution, a true one, would be taking every single combination of size n from the population. So that, generally speaking, is an incredibly large number from the population. And so we generally don't do a true sampling distribution, but we generally do an approximate. Okay, so just remember that is another place where you want to sound like you don't have the exact. But if we do this, we can think of our results in two ways. We can either think about our binomial formulas, where if we were to check that it was binary, independent, fixed number of trials, probability of success not changing because it was independent, then we could use our binomial formulas. And in the binomial formulas, our mu sub x is basically the expected count of our result, what we're interested in. And we have our expected standard deviation for what we're interested in. But since we're doing a sampling distribution of p hat, and since we know that p hat will be x divided by n, we can actually see that how our p hat will be our best guess at what we think the true population p-value is. So in this situation, you can see that we've got 1 over yeah. So we've got we can multiply the random variable x. Therefore, just multiplying the random variable x by the constant 1 over n will get us the random variable for p hat. So therefore, that's how these two formulas that we see here, which are going to be extremely important, are going to help us with the mean and the standard deviation for the sampling distribution of p hat. So what do you think will happen to your spread as sample size increases? So spread would be variation. So let's see here. Here's my symbol from the formula sheet for variation. And actually, let me show you the formula sheet so you can just see it on there. Okay, on this formula sheet, so get comfortable with this, always have it out. Here's our binomials. And then right below it, oh, that's our geometric. Guess I better turn the page then. Let's see what we have on the next page. Oh, there's on the next page, if we're looking for a p hat, our best estimate of the population value p and the standard deviation p times q over n. And then over here we have what's called the standard error of the sample statistic. It'll be, sometimes we're going to be using the sample values, but sometimes we'll be using population values, and we'll have to learn when we use one and when we use the other. So what do we think is going to happen as our spread as our sample size increases? So if you look at the formula, where our formula is, as your n gets bigger, as that n gets bigger, you're going to be dividing by a larger number. So what do you expect the standard deviation to do as your sample size increases? The spread will decrease. And what do you think will happen to the mean proportion of the sampling distribution? So let's look. Mu sub p hat is estimated best by the population value. As we change n, what happens to the population value? N changes, but does not affect p. Okay, so the mean is not going to be affected by changes in your sample size. Therefore, p hat is going to be our best unbiased estimator of the population proportion p. So if we don't know the population value, we will use p hat. So the results can be summarized as follows. You have a population, all these people, you take a simple random sample of size n, you get a p hat, then you throw the people back in there, do it again, take another p hat and another until you have this sampling distribution, but probably it's approximate, but of p hat. And what you notice about this is that it looks, what does the distribution look like? It looks like it is symmetrical, bell-shaped. But my question to you, is this enough to be nearly normal? Because if it is, then that would be very important and very helpful, because we could use so many of our techniques with that. So we're going to check the normal to see if we can use this. And how do we check that for proportions? We use n times p being greater than or equal to 10. And we would check n times q being greater than or equal to 10. Now look on this formula and you can see that if there is no hat on the p or the q, so if you have population values, that's what you'll be checking to see the shape. Then use them. Okay, and that would be to be able to be nearly normal. And then if we want to use the standard deviation formula for the standard standard deviation of the sampling distribution, then we have our formula off the formula sheet. P, they use n minus p, or 1 minus p, but I like q. What do we have to check in order to use this formula? We actually need the condition of independence must be true to use this formula. And so how do we check for independence? When we have finite things that we're pulling out of a population, the check is that our sample size is not over 10% of the population size. That means that our dependent probabilities are not a big enough change to change the probability. And in all these situations, make sure you explain how you checked and what you saw when you did the check. Okay, so now we'll do an example. And so we're going to go through and just see if we can identify what's been provided, what parameters, which are population values, what statistics. So 75% of young adult internet users between 18 and 29 watch online videos. Suppose that a sample survey contacts an SRS of 1,000 young adult internet users and finds 780 of them watch online video. So this is about the population. So I can write it with a population symbol like that. And you probably should define that P equals the proportion of young adult who watch online video. Okay, and then did we find anything else? It looks like they went out and they did a sample, and in that sample they found a p-hat, and it was 780 of them out of 1,000, so that's 0.780. Make sure you use at least 5 digits for your proportions if they don't come out to be exactly to the decimal. Okay, so what is the mean of the sampling distribution of p-hat? So we're going to look at the formula sheet. We're going to see if a condition is needed for this. For this, on our formula sheet, it says that the mean of the sampling distribution of p-hat will be p. So look up above, and which variable did you define as p? 0.75. So, and then of course I would write my answer in context. Mean of the sampling distribution of p-hat is 0.75, and that's that's the best unbiased estimator for that. Okay, next one. Now we're going to find the standard deviation of the sampling distribution. And I said to always be thinking about what conditions are needed to do these things, and to use this formula, which I'm just sliding it over just a smidge so that I can fit my condition. Whoops, sorry, P times Q over N. Okay. In order to use this formula, I need to have independence. And so, pendence. Okay, so, and the way to check it when you have a finite population, in this case, internet users, that's a finite population. Let's check if our sample size is less than or equal to 10% of the population size. 1,000 less than or equal to 10% of N, and I would say since more than 10,000 young adult internet users, since we have more than, I'd say there's definitely more than 10,000 young adult internet users, then we have fulfilled the independence condition and we can go on and find our standard deviation of the sampling distribution. So let's put the values in, and these do not have hats on them, so I will use the parameter values. And I punch that in the calculator and I get 0.013693. Now I've given you 5 significant digits, and I'm going to do that because I want, if I use this for anything, I want it to be not reduce my rounding errors. And then, of course, I'd say it in context. Standard deviation of the sampling distribution of p hat is 0.013693. Okay, is the sampling distribution of p hat approximately normal? Well, let's check the n times p being greater than or equal to 10 and n times q being greater than or equal to 10. And so we have 1,000 times, now what letter is there? P, 0.75. So 750, well that one meets, but does it meet on Q, the one with technically the lower probability of 0.25? Yes, 250 is greater than or equal to 10. We can say that the sampling distribution of p hat is nearly normal. And of course, you have to have something substantiating it, and I do by my calculations, which are right there. Okay, so using this above information, someone found the probability of p being greater than 0.78. And I could have also written it like this. It actually would not change the probability at all. So whether or not you have the greater than, or the greater than or equal to, it doesn't change the probability at all, because in continuous cases you can't find probability of a line. So that's what kind of conclusion would you draw from this value? I would say that this is much lower than 0.05. So since 0.0142 is less than 0.05, it would be unusual to get a proportion over 0.78, and then in sample size n equals 1,000, for young internet users, of young adult internet users who watch a video. Okay, if the sample size were 9,000 rather than 1,000. Would this change the sampling distribution of P? Okay. What would it do to the center? What would it do to that? That would stay the same. So the center would remain at 0.75. What would the standard deviation do? We now have increased our sample size. That's going to take our standard deviation, our variability, and it's going to decrease it. In order to use that, you still would need to be independent, and you would have had to check that 90,000 was less than or equal to 10% of n, and or 9,000 is less than or equal to 10% of n. And I think it is appropriate that there are 90,000 plus young adult internet users. That seems appropriate. So we would have then calculated our revised standard deviation of let's see, what would that new value be? 0.0045644. So let's see, I've looked at the center, and this would be my spread. Okay, shape, outlier, center, spread. So I've done my center and my spread, so let's think about our shape. And if I was working before at being nearly normal, now that I have my increased sample size, then then now I'm really meeting it. So definitely I am still going to be nearly normal. And so that would stay still nearly normal. Let's move that up. So shape was still nearly normal. Outliers doesn't really apply in this situation. My center remained the same, but my spread is narrower. Okay, another example. And this one, we've got a polling organization. We've got, they're going to ask a simple random sample of 1,500 first-year college students, how far away their home is. Suppose that 35% of the first-year students actually attend college within 50 miles of their home. What is the probability that a random sample of 1,500 students will give a result within 2 percentage points of this true value? Okay, so we're going to use the sample proportions technique. So we would start by thinking about our conditions. Is this random? And they said it was SRS was given in problem. Is this independent? Is n less than or equal to 10% of n? We are asking 1,500 students, 10% of n. In order for this to happen, we would need to have n would need to be 15,000 or more in population. I think that's probably reasonable for the because they're asking people, they're asking first-year college students in general. A lot of times, if it's for a specific school, they would have had to say a large college or a large high school. That would give you the information that it's, you know, that you have your independence. Okay, and now, like, if it's going to be nearly normal, and because it's proportions, we check n times p, n times q, and we have, let's see, oh, we never really set up what p was. I'm going to do that at the beginning here. Let's say that p is going to equal the proportion of first year students who attend college 50 miles, within 50 miles of home. Okay, and P, the true population value, we believe is 0.35. And it looks like we don't know what P hat is, but we want our result to be within 2 percentage points from that. So we'll look at that. But anyway, now that we know what P is, we can come down here. And if we didn't know what P was, we would check with our best guess at P. But we do know what P is. And if the 0.35 is working, then the 0.65 will be definitely working. But I guess I get in the habit of writing both of them. So that means I have met all conditions. So to use these formulas, so let's go up. That means I've met the conditions. So let's draw our normal curve, because that was the whole point of being nearly normal. And the middle of our normal curve will be our mu p hat, which from the formula sheet is p. So the middle of this curve is 0.35. And we just we haven't determined yet the standard deviation of our sampling distribution, but we did determine that we can do this because we have something that is independent. So why did I did that on the other page too. 0.35 times 0.65 divided by 1500, square root of that. And so I get, and I like to keep this thing really long because I'm going to be using it for so many, say 0.01231530021. Okay, so there's my standard deviation for the sampling distribution of p hat. And I want to be within 2 percentage points, so my high value could be 0.37. See, 0.02 away. My low value could be 0.33. And I want to know the probability of being in, let me double check. What is the probability that they are within? Yes, within this zone. So now I'm going to do my z-scores. Starting to feel familiar, hopefully. Now you're starting to see how, and this is what happens, it just starts coming back. Okay, let's use that number. 315302. Okay, so my z low was around negative 1.623996. My z high is going to be the 0.37. And so that is 0.323996. And then you can use your notation with the p-values or with the z-values. I tend to go with z just because then it applies in all situations, means or proportions. And I would probably just round that like that, right? Z, and then 1.624. And so my probability, and I'd use my normal CDF, left, right, 0 and 1 if I'm using z-scores. And if I was going to use the p-values, if I wanted to write it with the p-value, with the proportion values, I would write 0.33, and I would use a p in the middle, not a mu, a p, because I am looking for proportions here. And if I was going to use the 0.33 and the 0.37, I would use my true standard deviation. And I guess I'll show you on the calculator the two. If you know what to do, you can probably triple time me through this. Okay, so distribution, get all my distributions. There's my normal CDF. Why is this crooked? No. Okay, so left is negative 1.623996. Right is 1.623996. I probably could use the answer key really. And then I'm using 0 and 1 because those are z-scores. And there's my probability. So let's just double check that this is going to match. And I mean, you don't have to double check this. You could just use that. But, just to show you that you could use the other values, the 0.33 and the 0.37, but then 0.35 is my mean, and my standard deviation will have to go in here. So let me just have the calculator calculate that. So 0.35 times 0.65 divided by 1500, close my parenthesis, and go down and paste that, and it's going to come out exactly the same. So there's the probability of that happening. If you're using z numbers, you're using z mean and probability. If you're using, actually I don't need that. Okay, so point 0.8956. So if I was going to round that to 3 sigs at this point, it'd be 0.896. The probability of, let's see, of the random sample of 1,500 students. It's always a good idea to give your sample size. Will give a result within 2 percentage points of the mean, the true mean, or true proportion, is 0.896. Done. All right, so hopefully you're enjoying how it's starting to build on, and you're noticing some similarity from thing to thing.